Hello, everyone. Welcome to Pre-Lecture 27. We're going to continue with some electrochemistry in Chapter 17, looking at standard cell potentials in this video. Also, just before I get into the chemistry, a reminder that your part one of your faith integration assignment is going to be due by the end of the day, Tuesday, and that will be April 20th. So make sure you're getting that done, responding to the prompt posted on our Canvas page. Okay. So in class last time, we talked about voltaic cells, which can also be called galvanic cells. And in any sort of electrochemical reaction, in a galvanic cell, we have essentially a cathode and an anode. Cathode is the cell in which reduction takes place. So in this example here, that would be the cell on the right, where we have dissolved silver that is becoming silver solid. So it's being reduced at the cathode by the flow of electrons coming from the anode. So at our anode, again, our copper in this case would be changing from solid copper metal to copper 2+, which is, of course, an oxidation taking place at the anode. Okay. So moving on from that, we oftentimes want to know then how much electrochemical potential can be produced by an electrochemical cell. And so it's simple enough to calculate. You just take the potential of the reduction half reaction happening at the cathode, subtract the potential of the reduction, or I guess the oxidation reaction rather, occurring at the anode. Okay. And so if we were to put this on a scale, which is what is commonly done, the standard hydrogen electrode, what's called the SHE, is used to establish that scale. And so essentially the potential of the reduction or oxidation of hydrogen gas on a platinum electrode under these conditions where we have H2 gas at 1 atm and a 1 molar concentration of H plus in solution. Those are our kind of standard conditions that sets our chemical potential at 0 volts. Okay. If we then were to hook up that standard hydrogen electrode to any other sort of half reaction, we could measure the standard reduction potential. And so the standard reduction potential for any sort of compound, or what we'll mostly be looking at as different metals, is basically the reduction potential, the potential relative to our standard hydrogen electrode that the electrochemical reaction will occur. So in our example here, again, on the left, we have our standard hydrogen electrode. We can measure the potential difference between that and the, in this case, reduction reaction going on with copper. And so in order for that to happen, you need to be 0.337 volts more positive than the standard hydrogen electrode in order for that chemical reduction to occur. Okay. And fortunately, most of these values have been tabulated, and that is a fancy way to say that they are all in a table. So table 17.1 in your textbook, as well as Appendix L in your textbook, have a list of the standard reduction potentials. These are just some of the more oxidizing potentials. So we go all the way up to fluorine gas that is extremely oxidizing, and then all the way down to lithium metal, which is extremely reducing. I will also say as a side note that because lithium metal is so reducing, that's why we have the advent of such technologies as lithium ion batteries. So we've been able to harness that electrochemical potential of lithium being reduced to lithium metal, and we're able to use that in the construction of battery materials in order to produce basically high-powered and long-lasting batteries. Okay. So within these reduction half reaction tables, I should also point out that every reaction here is written as a reduction reaction, meaning that we have our electrons as our reactants. So that is just the convention for the field of electrochemistry. That's why we would also call this a standard reduction potential, because we are looking at the potential at which electrons will be added to a species to make some sort of product. Okay. And so species towards the top of this table have more positive reduction potentials, meaning they are more easily reduced. That would also mean they are better oxidizing reagents if we were to use our vocabulary that we learned from last lecture. And then species towards the bottom here, so all the way down to lithium metal, are more negative, have a more negative reduction potential, which means they are more easily oxidized or better reducing agents. Okay. So here's an example for you. What was the cell potential for electrodes that would be made out of silver and barium? And then a sub question of that is what is oxidized and what is reduced between those two metals if we were to set them up in an electrochemical cell. So take a moment to think about that. If you want to pause the video, you can, but I'm going to go ahead and answer it right now. So if we think about this, the first thing we would want to do is compare the reduction potentials, or standard reduction potentials, I guess I should say. And so silver is more positive. If we look here, our silver reduction potential is 0.7996, whereas our barium reduction potential is minus 2.912. Because silver is more positive, that means that it will be what is oxidized during our chemical reaction, right? Oh, sorry, I believe I flipped that there. Whatever is more positive will be reduced, and then whatever is more negative will be oxidized. So if we think about that with regards to the equation that we learned here, that means because the silver reduction potential is more positive, it will be reduced. That would mean we keep this electrochemical equation the same way, where we have electrons as our reactants, and then barium would flip. So that would mean that our reactant would be solid barium metal, and we would be oxidizing it to barium 2 plus and getting 2 electrons as products, meaning that we would ultimately be subtracting a negative, and that our overall cell potential then would be 7.7116 volts. Okay. You should also note that the cell potential will always be positive for any sort of spontaneous cell. So whether or not a cell is spontaneous just depends on which direction the electrochemical reaction is proceeding. And in order to have again, an electrochemical cell be spontaneous, you will need a positive potential. Okay. And so ultimately that discussion of spontaneity should ring a bell for you, and we can actually relate our reduction potentials back to our Gibbs free energy as well as our equilibrium values, so our K values, equilibrium constant K, because they're all ultimately measures of a spontaneous process. And so if we use these two equations for these electrochemical cells, we can relate the potential of our cell back to our equilibrium constant K. We can also relate it to, again, here's our standard cell potential, relate it back to our Gibbs free energy. So the one thing, or the two things you may need to know here, each of these reactions has a constant n, which I guess is not a constant, it's a variable. So n is the number of electrons transferred during an electrochemical reaction, whereas F is a new constant for us called Faraday's constant. And that is 96,485 coulombs per mole of electrons. Okay. And finally, something that hopefully you noticed, but I of course would want you to know in case you did not, is that this E standard cell is the potential of an electrochemical cell in volts, which volts are also joules per coulombs, as another way we could represent that in order to make all of our units work. Okay. So ultimately, this means that we can relate, again, our Gibbs free energy, our equilibrium constants, and our electrochemical cell potentials. Our measures of spontaneity will be consistent throughout these. And so just as we've discussed in our previous units, and as well as chapter 16, any K value that is greater than 1 will produce more products than reactants, meaning that that reaction would be spontaneous towards the products. Any delta G value that is spontaneous will be negative. And then what we're adding in today is that any electrochemical cell potential will be positive if the reaction is spontaneous. Okay. All right, we'll continue to expand upon this in class on Tuesday. If you have any questions, of course, feel free to email. Otherwise, you can ask in class, of course. I hope you have a good day, and I will see you soon.